Welcome to the wonderful world of astronomy. This is the beginning of Chapter 7, Our Planetary System, and this is Part 1, a brief introduction to our solar system. We've spent the semester so far looking at a general overview of astronomy and also learning the fundamental principles of physics and chemistry needed to understand astronomy. And now we're getting into the in-depth study of the things out there in the heavens. And we're going to start local, looking at our solar system. And as the semester goes on, we're going to branch out looking at other stars and other star systems throughout the galaxy, and then eventually other galaxies and the universe as a whole. But let's start now with an introduction to our solar system. I want to show you a general layout of the solar system. This is a picture taken from the textbook, and you can see general layout here. We've got the sun at the center and planets orbiting around the sun. None of this is to scale of size. The sun actually is by far the largest thing in the solar system. But you can see here the layout. You have the sun, you have the planets going around the sun, and right here it shows an asteroid belt, a belt of asteroids between the orbits of Mars and Jupiter. And then farther out, you have what's called the Kuiper belt, which is a belt of comets going around the sun at a very large distance beyond where the planets orbit. This is a simulation of the solar system. And this is actually what's called the inner solar system, which is the sun and the first four planets. So we have the sun at the center, the orbits of Mercury, Venus, Earth, and Mars. And we learned in chapter 3 that it was discovered that these are not circular orbits, but rather they are elliptical orbits. You can see some other things, some little dots with names on them. These are just stars that are way off in the background, so you can ignore those. Those are not part of the solar system. You've got the large purple grid here, and the grid represents the plane of Earth's orbit, so it's the ecliptic plane. And in a bit, I'll show you as we tilt this entire star system, we'll be able to see the grid in another angle. We're going to zoom out now, and here we have just on the edges the orbit of Jupiter. Let's zoom out some more. You can see Saturn's orbit. And we keep zooming out, and here we have Uranus's orbit. Let's go one more, and now there's Neptune's orbit. You can see that as we move farther and farther out from the sun, the distances between the planets get progressively larger. And so it is 1 astronomical unit from the sun to Earth, which is this green circle right here. And then it's 5 astronomical units going out to Jupiter. And then it's 10 astronomical units out to Saturn. So the distances get progressively larger between the planets. And we continue to go, and now we've included Pluto's orbit. Let's go one more. And here we have all of the planets plus Pluto going around the sun. And now let's tilt the plane. And so now you can see, looking more edge on at the ecliptic plane, which is represented by the purple grid, you can see that the planets are fairly close to that same plane. Now, Pluto is an exception, but remember, Pluto's not a planet anymore. It was declassified in 2006. And later on in chapter 7, we'll look at why it was that declassified. But the 8 planets that are now recognized, they're all in pretty much the same plane. Let's tilt it one more time. And there they are. They are, for the most part, in the same plane. The blue one that dips down a little bit, that's Neptune. But you can see they're pretty much in the same plane, and Pluto is oriented away from the plane. So let's talk about what the solar system looks like. We've already talked about the planets going around the sun and the asteroid belt. The asteroid belt is a belt of asteroids that is between the orbits of Mars and Jupiter. It's where most asteroids in our solar system are. There are other asteroids in our solar system. Notably, there are what's called the Trojan asteroids. So this is a group of asteroids that are 60 degrees in front of Jupiter and 60 degrees behind Jupiter. Trojan asteroids is a general term that sometimes refers to any group of asteroids that shares the orbit with a planet, but the originally discovered Trojan asteroids were the ones in Jupiter's orbit. Sometimes they are distinguished. The ones on one side of Jupiter are called the Trojans, the ones on the other side, the Greeks, an allusion to the Trojan War. However, in general, I'm just going to call them both groups Trojan asteroids. You can also see all these speckles throughout the solar system or the inner solar system. There are many asteroids that aren't contained in the asteroid belt or in the Trojan asteroids, but most asteroids are primarily in the asteroid belt and secondarily in the Trojan asteroids. There are also comets that are balls of ice that are in orbit around the sun. And let's look inside this red rectangle. You see the sun, the orbits of the planets, the one that's askew, that's Pluto's orbit. And just starting beyond Neptune's orbit is the Kuiper belt. It looks kind of like the asteroid belt, but it's just larger. It starts about 30 astronomical units away from the sun and goes to about 100 astronomical units. And it contains comets, which are big balls of ice. Now let's zoom out. This red rectangle containing the planetary system and the Kuiper belt is right here in the middle of the Oort cloud. The Oort cloud is a spherical shell of comets that might be as large as 1 light year in radius, which is very large for solar system standards. That means that it goes out to about a quarter the distance to the next closest star. And so this is where many comets, most of which never come anywhere close to the planet, stay in orbit. So the main places where we see comets are the Kuiper belt and the Oort cloud. And we will talk more about comets and asteroids when we get to chapter 12. Now, there are other comets that aren't in either the Kuiper belt or the Oort cloud, and these are referred to as short period comets. So here we have, this is an animation of Halley's Comet, and it goes out as far as Neptune's orbit, just a little beyond Neptune's orbit, which is where the Kuiper belt starts. And you see, based on conservation of angular momentum, how when it is closer to the sun, it goes faster, it's farther from the sun, and it goes slower. Now, Johann Kepler figured this out about planets' motions back in about 1610. He didn't know about comet motions, but later on it was discovered comets do that also. And this follows under Kepler's second law of planetary motion. When it's farther away, it goes slower. And when it's closer to the sun, it goes faster. When we study planets in chapter 7, we're going to get into comparative planetology, which is comparing planets. We can learn more about a world like our Earth by studying it in context with other worlds in the solar system. We're going to stay focused on the processes common to multiple worlds instead of individual facts specific to a particular world. So I will teach you facts about the planets, but we're not going to get into needing to memorize the masses and the diameters and the axis tilts and all these quantities about the planets, but rather we're going to think about what patterns exist between the planets as a whole. Comparing the planets reveals patterns among them, and those patterns provide insights that help us understand our own planet. I want to think about the scale. When we look at, we make models, such as you can see this ping pong ball and the marble, to try to visualize where the planets, where the stars, where the sun, galaxies, whatever we're going to be talking about in astronomy, it's good to find a scale to picture because lots of times in drawings and in pictures in the book, it says this is not to scale. And so it's helpful to think occasionally of what is a proper scale. And so here's a good scale to keep in mind between the Earth, the Moon, and the Sun. We're going to imagine the Earth to be a table tennis ball, like you see on the left, and the Moon is a marble. So that is a proper size comparison of the Earth and the Moon. So we take a table tennis ball and a marble, hold them 4 feet apart from each other, and that is now the scale of the distance between the Earth and the Moon. Now, in this scale, the Earth being a table tennis ball and the Moon being a marble, holding them 4 feet apart, let's include the Sun in all of this. The Sun is much farther away from us than the Moon is, and it's much larger. So for the Sun, we're going to need a ball that's actually probably bigger than this ball in the picture. 14 feet in diameter would represent the Sun, and we would need to place it 470 meters away, or almost the length of 5 football fields. That would be a proper scale model between the Earth, the Moon, and the Sun. Here is a picture of the sizes of the planets. The sizes are to scale, the positions are not correct, but you can see the Sun, by far the most dominant feature in our solar system, and then the small planets, Mercury, Venus, Earth, and Mars. And these are in order of distance to the Sun. So Mercury is the closest planet, then Venus, then Earth, and Mars. And as you go through chapter 7, I expect you to memorize the order of the planets. So we start with Mercury, Venus, Earth, and Mars. And then we get to the outer planets, Jupiter, Saturn, Uranus, and Neptune. Notice that the 4 closest ones are the small ones. The 4 farther ones are the large ones. And we'll talk about why that is in chapter 7 and on into chapter 8 when we look at theories about the formation of the solar system. This picture also includes Pluto, which used to be a planet until the year 2006, and something else called Eris, which is out there beyond Pluto's orbit. We'll talk about that in a later video in chapter 7. Here also is the planets. These are all photos of the planets, and they are drawn to scale of size. So you can see Jupiter is the largest one, and then Saturn, then Uranus, then Neptune, and then in here we have Earth and Venus and Mars and Mercury. Now the reason they chose to make the slide like this is just to show that between Earth and the Moon, there's enough space. Now it is, as it says up here, about 238,000 miles between the Earth and the Moon. But that actually is, if you could line up all the planets, they would fit right between Earth and the Moon, as you can see here, with a little bit about 5,000 miles to spare. That is the end of our introduction to chapter 7. Have a great day.